Okay, reaction mechanisms. I'd like to share a little story with you. Thinking back to my great Uncle John's farm in Georgetown, where he grew strawberries and asparagus, we would have large family gatherings there. And I can remember my great Aunt Mary making these amazing dinners, meals, and there would be tons of kids and cousins around. And there's always the cleanup in the kitchen of the old farmhouse. So you can imagine there's no dishwasher there. There's lots of dishes, lots of people. And there's one sink, and so there's one person washing dishes, and there's like 10 kids lined up with tea towels ready to dry all these dishes. So that's why I'm saying imagine here, because I'm going to introduce this idea of reaction mechanisms, imagining yourself being in that farmhouse kitchen. So we started off with all of the dirty, dry dishes. Now, do they actually become clean, dry dishes immediately, like in a single step? And certainly you can imagine that no, someone's going to need to wash them and someone's going to need to dry them. So let's write a series of steps to actually communicate how the dishes are cleaned. So we start with dirty, dry dishes. And of course, the first step is for the washer to wash them. So how would you describe the dishes after they've been washed? Hopefully you're thinking they're clean, but they're not dry yet, right? So they're clean, wet dishes. Okay, so imagine the sink has these clean, wet dishes, or the counter beside the sink after they've been washed, and now all the kids are lined up there just chatting and waiting for the next dish to dry. So the kids will pick up those clean, wet dishes and they'll dry them. And so at the end of that, we have clean, dry dishes. So what I'm trying to give you an analogy for here is the concept of a reaction mechanism. The idea that an overall reaction, which I've said is here, the dirty, dry dishes becoming clean, dry dishes, actually doesn't occur in a single step. Knowing the overall reaction doesn't actually tell us how the products are formed. A mechanism, though, proposes how the products are formed. So, for example, we have the wash step, and then we have the dry step. So, if you look at the terminology below, you'll see the reaction mechanism I've defined for you as a series of elementary steps that predict how the reactants are converted to products. So this is a mechanism. It's a two-step mechanism. You'll see that the dirty, dry dishes become clean, wet ones in the wash step, and then we have the dry step. So I mentioned this term elementary step. So what is an elementary step? Well, a one-step process in which product particles are formed as the result of, usually, collisions between two reactant particles. So we would call that a bimolecular collision. To have three particles collide with the correct collision geometry, you can imagine is pretty statistically low in terms of occurrence, and that's why the trimolecular collisions are rare. So in the mechanism that I've illustrated up here, there's essentially two elementary steps. Now, in terms of these being bimolecular or trimolecular, well, really we'll have to discuss that in the context of an actual chemistry example. Unimolecular collisions can also occur. That's where one reactant particle decomposes. For example, ultraviolet light could be breaking the bonds within that molecule to cause that decomposition. So we'll look at some specific chemistry examples in a moment. I'd just like to go back up to my dish washing and drying mechanism just to show you that when you algebraically add the steps in the mechanism, you'll find that the clean, wet dishes cancel and that the mechanism, those elementary steps, do add up to our overall equation. Okay, so moving on now to a chemistry example. Example 1. So here's a proposed mechanism. I'm going to ask you to algebraically add those equations as written and write the overall equation. Check in with the video when you're done. This is not Hess's law. You do not have to manipulate these equations. Just cancel anything that can be canceled and group like terms and write your overall equation. Okay, so you can see that the H2O2 canceled out on the left and right side, and as I add my left and right sides, I come up with 2 nitrogen monoxide plus 2 hydrogen gas, produce nitrogen gas and 2 water vapor. Okay, so use the terminology that you've learned so far, indicate elementary steps in this mechanism, right? The actual mechanism itself, and the molecularity of each of the steps, whether they're uni, bi, or trimolecular. Okay, so you'll see that I indicated that these 2 steps together form a mechanism. Each of those elementary steps is indicated. There are 2 steps, and they form the overall equation. Now, in terms of molecularity, look at the number of particles colliding in each elementary step. So in the first step, we have 2 NO and 1 H2. So together, that would be a tri-molecular elementary step. If you look at the second elementary step, there's 1 H2O2 and 1 hydrogen gas particle. And so this elementary step is bimolecular. Okay, so just to be clear on what this mechanism means, when we look at the overall equation, it says 2 NO gas and 2 hydrogen gas react to form nitrogen and 2 water vapor. There's no way that 2 nitrogen monoxide particles and 2 hydrogen gas particles are colliding with the correct collision geometry and required activation energy to produce products. 4 particles to collide with the correct collision geometry is statistically impossible. So someone has proposed, based on experiments, that 2 nitrogen monoxide particles will collide with 1 hydrogen gas particle. Now that's a trimolecular collision, and we expect the rate to be pretty slow because it will be difficult to achieve the correct collision geometry. When that happens successfully, nitrogen gas, 1 particle, and hydrogen peroxide particles formed. That hydrogen peroxide particle then collides with another hydrogen gas particle in order to form the 2 water vapor molecules. And so that summarized the net effect in the overall reaction. But each of these steps is proposing exactly which particles collide and describing how the reaction proceeds. So you'll notice that H2O2 was produced in one elementary step and then consumed in another. And that's what we call a reaction intermediate, a substance that's formed in one elementary step and subsequently consumed in another step following that one. Now, I mentioned the trimolecular collisions here would be rare, and so this first step is going to be very slow. The rate determining step is the slowest step in the mechanism. So how fast will these reactants convert to products? Well, it's going to entirely depend on the rate of the slowest step in the mechanism. So the rate of this step here, this elementary step, the first one, will determine the rate of the overall reaction. Okay, now that's a significant statement here. So what I'd like to show you is that when we calculate the rate law of an elementary step, we actually use the coefficients in the balanced equation as the exponents. And you're thinking, but wait a second, we weren't supposed to do that before. That's because before you were working with overall equations without really realizing it. And so these coefficients are not necessarily the exponents. But when you're talking about an elementary step, you are referring to the number of particles that are actually colliding. So these coefficients are the exponents. They do indicate the sensitivity of the rate to changes in that concentration. So use the exponents of an elementary step as the exponents in the rate law of that elementary step. And so the rate law for the first step in this mechanism, and I'm just using a subscript of 1 here to indicate it's the first step, would follow like this. Now, what would the rate law equation be for the second step of that mechanism? I'm just going to erase this so that I have a little bit more space here. So for that second step in the mechanism, the rate law is going to be the reaction intermediate concentration raised to the exponent 1 and the hydrogen gas concentration raised to the exponent 1. Okay, so for elementary steps, right, we use the coefficients for the exponents in the rate law. All right, so we've said that the first step, being trimolecular, is anticipated to be the rate determining step, the slowest step. And so the final point here is that the rate law of the rate determining step is, and you'll see when you work out problems, is equal to the rate law equation of the overall reaction. And so the rate law equation of the overall reaction is expected to be K times the concentration of NO squared times the concentration of H2 to the exponent 1. So if we had a table of rate law data or rate experiment data, we would determine the exponents in the rate law and find that NO, it's second order with respect to NO and first order with respect to H2. So the idea is that this comes from experimental data, which is what you were doing in yesterday's lesson with all those tables. And the point is that it will match the rate law equation of the rate determining step in the mechanism. And so here's the connection between yesterday and today. All right, so it seems a bit complicated. Let's go through another example. So I'm asking you in example 2, this is a well-studied mechanism, by the way, experimentally. So I'm asking you first to look at this mechanism and write the overall equation, noticing that Cl2 decomposes to 2 free chlorine atoms. So energy is required to break that bond for sure. One of those chlorine atoms then reacts or collides with a hydrogen gas particle to form one particle of HCl and a free hydrogen atom. That free hydrogen atom then collides with another Cl2 molecule to form another HCl and a free chlorine. And then the two remaining free chlorines, one from here and one from here that hadn't reacted yet, recombine to form Cl2. So go ahead and cross out any reaction intermediates and write the overall equation. Okay, so you'll see that the Cl2's canceled, the free chlorine atoms canceled, the free hydrogen atoms canceled. And we have H2 plus Cl2 produces 2HCl. All right, just as another quick question here, what do you indicate the reaction intermediates? So what are the reaction intermediates here? Hopefully you're thinking of the free chlorine atoms that were produced in the first step and then subsequently consumed, used up in another step, as well as the free hydrogen atoms that were produced in the second step and then consumed in the third step. Okay, so we have our 4-step mechanism. The first step is unimolecular. The second step is bimolecular. The third step is bimolecular. And the fourth step, 1 plus 1, is bimolecular. Okay, so I'm just reviewing the terminology that we've learned in the lesson. And we have the mechanism. All right, so I'm giving you now this information that the rate law of the overall reaction is rate equals K times the concentration of Cl2 to the exponent 1. And I'm asking you which step is the rate determining step. So you're being given the rate law of the overall equation right here. So that has been determined from experimental data, from tables like you did in the previous lesson. So which step do you think is the rate determining step? You're looking for the slowest step, which determines the rate of the overall reaction. And if you'll recall from what we wrote up here, we saw that the rate law of the overall reaction from experimental data will match the rate law equation of the rate determining step. So, what do you think? So, you'll notice that I wrote the rate laws of each of those 4 elementary steps. I am using the coefficients here as the exponents because they are elementary steps. You cannot do that for the overall equation. Okay, so which elementary step has the same rate law equation as the overall reaction? You'll have noticed that it's the first step, so the first step in the mechanism is the rate determining step. Okay, I'll take any questions you have with that tomorrow. Potential energy diagrams. Now we're going to finish the detail in our potential energy diagrams. I'm asking you in this potential energy diagram to now label reactants, products, delta H, the activated complex, which you can indicate with the letters AC here, activation energy, the rate determining step, whether it's endo or exothermic, and the potential energy of any reaction intermediates. Okay, so give that a shot and check back with the video. Okay, so I've almost finished labeling this, but I thought I'd better start talking through it to help you along. So, reactants and products I've indicated, and the difference then between the products and the reactants is delta H, the enthalpy change. We notice that that's negative here, and so it's an exothermic reaction. So, moving into these humps here, the fact that there are 3 peaks here means that there are 3 steps in the mechanism. And you can see that each, as you read this blue curve from left to right, that each step has its own activation energy. And so moving from the reactants, right, up the hill to the first activated complex, so of the first elementary step, we realize that this is the activation energy. Now I've indicated it as EA because I don't have enough room to write the C and T, but I'll call it EA1, meaning that it's the activation energy of the first step. After that activated complex is formed, right, then a reaction intermediate would be formed and collide again with other reactant particles to continue into the second step of the mechanism. So this small little arrow here right now represents the activation energy of the second step. And an activated complex is formed as those product particles, as reactants start to break bonds and particle bonds start to form. And we dip down again to form another reaction intermediate. As we continue into the third step of the mechanism, the potential energy rises again as a new activated complex is formed, and this small arrow would represent the activation energy of the third step. And then following that, products are formed. So we have 3 steps in the mechanism as determined by the 3 humps. Now, which activation energy is the greatest? The activation energy for the first step, for the second step, or the third step? Hopefully you're seeing that this distance is the greatest. When the activation energy is the greatest, is that step fast or slow? So does a high activation energy correspond to a faster rate or a slower rate? Just to jog your memory, remember the Maxwell-Boltzmann distribution, having the number of particles there and energy here, that when you have a higher activation energy, EA1 for example, compared to a lower activation energy, EA2, isn't it true that the area under the curve past EA1 is really quite small compared to the area under the curve for EA2? And so the higher or larger activation energy corresponds to a lower percent of effective collisions, which is then going to lower our rate. And so we would expect step 1 to be the slowest step. So the rate determining step is step 1 of the mechanism. Okay, good luck with that. I'll see you tomorrow.